Typically in robotics, robots get a continuous feed of images through its camera. So it is mandatory to be able to read a video stream. OpenCV library supports this functionality. It is possible to read video streams from cameras or from video files, and also to save them to some other files. In this video, I'm going to show how we can read a video stream from USB cam and also from a video file. Let us consider the file readvideo.py. So as usual, we need to import NumPy and CV2 library and OpenCV library. And then, in order to capture a video stream, we're going to use the method video capture of the OpenCV library. So video capture can be applied either to read from a camera device attached to the computer or also to read from a video file. So here, for example, when we put 0, it means we are going to connect to the first video device connected to the computer. So on a computer, it's going to be your USB camera. And as a video stream is actually a collection of images, we need to have a while loop to read the frames coming from the video stream. So here we go for an endless loop and we use the video capture object that we have created here and the method.read. So read is going to return one image from the video stream. It's going to read image by image and we will return them one by one. And later on, we can just use the frame like any image that we read from an image file. So here, for example, we can display the image or the frame received, and then we will have some delay between one frame and another. So usually we can play with this delay depending on how fast we want the video to be played, and this is expressed in milliseconds. So if I make a delay of 1000 milliseconds, it means every second I'm able to process one frame. So here, for example, we are going to see only one frame per second. However, if we want to have a smoother video stream, in this case, we can put it at very small value, for example, 10 milliseconds. And finally, we're going to wait for the key Q to be pressed in order to break the loop and close the program. So here we release the video capture and we destroy all the windows that are on. So let us run the script now and see what happens. So you can see now the camera has opened and I can play my hand. So you can see my hand here moving smoothly because we have put a very small delay. Let's try now to increase the delay. I'm going to press Q to leave the program. And now I'm going to put 1 second delay between one frame and the other. Now we can play again. So you can see now there is much bigger delay to update the motion. So the motion becomes less smoother than before because we put 1 second delay between one frame and the other. So the delay is not visible here. It is also possible to read the video stream from a file. So here, instead of reading from the camera device, we can specify the path to a video file, and then using the same while loop, we will read the file frame by frame, and then we will show every frame in the window. So we can try now to run this file. So you can see now this is the video running. Now it's going to be very slow because here we have put a key equal to 1 second. So let me put this one at 1 millisecond, and then we try to run again. And by the way, the length of the file is around 3 minutes. So you can see when I put the wait key equal to 1 millisecond, the file is going to be executed pretty much fast. Now, instead of having 3 minutes of length, it's going to run only in a few seconds. This is because we process the frame very fast, 1 frame per millisecond. So here you need to carefully adjust the value of the delay, and usually 25 milliseconds would be an appropriate value. So you can see now the video is executing. 3 minutes length video is going to execute in only a few seconds. We can also do some image processing before showing the video. For example, here, if I would like to convert the image to gray color, okay, so you can see now the video is going to be black and white or grayscale color. You can also resize. You can do any kind of processing on the frame before displaying, or okay, so now we have resized to 50%. So in this video, we have demonstrated how we can open a video stream with OpenCV, either from a USB camera or from a video file. One of the nice features of OpenCV is the ability to draw shapes. It's possible to draw circles, rectangles, lines, polygons, and different kinds of shapes. So let's see how it works. So let us consider this very simple script. Here we import NumPy and OpenCV libraries, and then we create an image using NumPy.zeros. So NumPy.zeros is going to create an image where all the values are zeros in this data structure of 512 pixels by 512 pixels and containing 3 colors each, red, green, and blue. All of them will be set to 0, so we're going to have just a black image. And this is the encoding of the image. It will be on n-signed integer over 8 bits. And with OpenCV, we can draw different shapes. For example, we can draw a line, we can draw a rectangle, we can draw an ellipse. So for example, when you want to draw a line, you have to specify in which image you want to draw the line. You need to specify the start pixel of the line and the end pixel of the line, and then the color of the line. So here it's going to be white color because all the 3 RGB values are equal to 255, and here the thickness of the line. For the rectangle, it's also simple. You specify the image where you want to draw the rectangle, and here we specify the coordinate of the left top corner and the bottom right corner. And here the color of the line of the rectangle, which will be green in this case, and finally the thickness. Same thing also applies for the ellipse, and here we specify the coordinate of the center, the major axis length and the minor axis length, the start angle and the end angle, thickness and the color as well. It is also possible to draw polygons, and polygons are specified by an array, and this array will be provided as an argument to polyline functions in OpenCV to draw a polygon. And also it is possible to put a text where you specify the location of the text and the font that will be used. So here we use the font, we use the following font here, and then the color of the text and the thickness of the text. And finally, we can show everything into the image. So let's try to run this example, image draw, and here let's look. So this is our line starting from 0 to the last pixel here, and it has a white color. This is our rectangle here. It is in green, as you can see, with the coordinates specified. We specify the left top and the bottom right. And this is our polygon here in the yellow color. And we have an ellipse in blue color. And finally, we have the text in the white color here. So you can see OpenCV also provides functionality to draw inside an image. So one of the uses of drawing is, for example, in object recognition, you can use rectangle to surround the object detected and recognized. So far, I have introduced several functionalities of OpenCV, and every time we read the images either from files or from camera devices, but directly using OpenCV functionalities. However, in ROS, images are collected from the topics that are published by the drivers of the cameras. So we don't have direct access to the cameras to be able to use the OpenCV functionalities, but we are going to receive the images from ROS topics. So in this case, we need to create a subscriber in ROS in order to receive the image and then sending this image to OpenCV for further processing. However, we have a challenge here. That is, the image format supported in ROS is different and not compatible with the image format supported by OpenCV. For this reason, there is a need to transform any image coming from ROS into the format of OpenCV, and vice versa also. When we want to publish an image coming from OpenCV, we need to transform it to the format supported by ROS. Fortunately for us, there is a special component called CV Bridge that allows to make this conversion from ROS format to OpenCV format and vice versa. So this is the architecture of CV Bridge. So basically, this is the ROS ecosystem here, and you have images collected through topics and are sent into image messages. So this is the format supported by ROS. And we want to process this image using the OpenCV library. So processing directly the image received is not possible because OpenCV library does not recognize the image format in ROS. So what does the CV Bridge do is going to transform this image into a format that is understood by OpenCV. After doing this conversion, we can apply any OpenCV functionality to the converted image. And also, if we have an image in OpenCV and we want to send it through a ROS message, CV Bridge can also do the opposite transformation. So let's see how this works in practice. You can find the code that allows the transformation between ROS image format and OpenCV image format in the file called imagepub.sub.py. So as usual, we have to import ROS.py, OpenCV libraries, and different messages here. So the first thing that we need to do is to create a bridge. So a bridge, this is an object that will make the transformation between ROS image format and OpenCV image format. So we use the class CVBridge, so this is the constructor, and we create this object for later use. And now we have our main program. We're going to initialize a node. I'm going to call it image converter, and then simply create a subscriber to an image. I will call it image subscriber. It will subscribe to a particular topic. So here we put the topic on which we are going to receive the information from. For example, I'm going to use a webcam. So the webcam topic would be this one. We are going to verify this later when we run the program. And here we have to specify the type of the message in ROS. So in ROS we have the type image, and looking at the documentation of ROS, we can find all the information of the image message. It has a header, it has the height of the image, the width of the image, the encoding used for the image, and whether it is big Indian or not. And finally, most importantly, all the data of the image is carried out here in one array, okay? An array of unassigned integer over 8 bits. And then we call the image callback. So whenever we receive an image through this topic, we're going to execute the image callback, okay? So in the image callback, we will have an image in the ROS format, and we want to transform this image into OpenCV format. So when we receive the image, okay, we're going to use the bridge that we have declared here above. So use it as a global variable. It can be also declared inside the callback if needed, but no need to create every time a new object. We can create it only once and then use just a global variable here to work with the object. And then based on the ROS image collected through the topic, we're going to create CV image for OpenCV image, and we use the bridge and then image message to CV2. So this is the method that we are going to call from the object bridge in order to convert from the ROS message that we received on the topic into the OpenCV message. And here we put the ROS message and which format we want to convert to. So we want to convert it into HER format encoded on 8 bits. And finally, we can throw an exception whenever there is an error that happens for this conversion. And then after this point, anything you do on OpenCV, you can do it. For example, I can run cvimage.shade because now we have a NumPy array. So I can get the shade, the number of rows, the number of columns, the number of channels. I can also print circle. For example, this is just a condition if the columns number of rows greater than 200. In this case, I can print a circle into this location and in this color and so on. So I can print also a text. So anything we can do with OpenCV, we can do it after this point, after this conversion. So this is the only thing that CVBridge does for us, is just to make the conversion between the ROS image into an OpenCV image format, and then we can call any method in OpenCV. So let's run the code now. Okay, first of all, we need to run the camera. Okay, so let me first run a ROS core to start ROS, and then on another terminal, we're going to run ROS run USB cam node, and then we specify the pixel format is equal YUYV. So this is actually important because if you don't do it, the node may not be running correctly. So let me start the camera now. Okay, so it's now running. I can verify, I can make ROS topic list, and here I can find the topic called USB cam / image ROS. So this is the topic we are going to use to receive an image from ROS. I can actually verify that the camera is working fine. I can run ROS run image view, and then image equal, and then I can specify this topic. Okay, so now it's running. So now it is ready that we run our program here, and we make sure that we are subscribing to the correct topic. So remember that the topic name is USB cam / image raw, and this is the topic that we are subscribing to. Now we run ROS essentials image pub.sub.py. Okay, so you can see now the webcam is running. Okay, so this is when an image comes through ROS, it will be converted to OpenCV, and then I will draw a circle. So this is the circle drawn. You can see it here, and this is the text webcam activated. So you can do any OpenCV functionality just after making the conversion. So in this video, we have presented the functionality of CV Bridge, which is very important, that allows to convert an image from ROS format to OpenCV format, and also it allows to make the conversion in the opposite direction. Now you have all the ingredients to do image processing with ROS and OpenCV. You know how to subscribe to an image, and you know how to convert an image to OpenCV format, and then you can explore the big ocean of OpenCV in order to make any kind of image processing, like for example image segmentation or thresholding or edge detection or image detection and recognition, any kind of functionality. In this video, I'm going to talk about thresholding, which is the simplest method of image segmentation. The principle is very simple. We start from a grayscale image, and using thresholding, we produce a binary image, either black or white. So the process is the following. If a pixel is greater than a threshold value, then it will be assigned a certain value, for example 255, to assign it as a white color. And if it is lower than a threshold value, then it will be assigned to another value, for example 0, to make it black. And there are two different types of thresholding: the simple thresholding and adaptive thresholding. Simple thresholding, it uses the very simple formula, as I already explained. If the pixel is greater than a certain threshold value, then it will be assigned to a white color, 255, and if it is smaller than a threshold value, it will be assigned to a black color, to 0. And in OpenCV, we use the method cv2.threshold, and it takes as input the gray image itself, and then the threshold value, which is a value between 0 and 255, the maximum value. So typically in a grayscale image, the maximum value is equal to 255 because the color is encoded on 8 bits. And finally, the threshold style. And there are different threshold styles predefined in OpenCV. We have a threshold binary, which is very simple. So for every pixel at position X and Y, if the value of the pixel is greater than the threshold, then we will assign the maximum value, which is 255, which means white color. And if the value of the pixel is smaller than the threshold, we will assign 0. Another style is threshold binary inverted, and here we will do the opposite. If the pixel value is greater than the threshold, we will assign it to 0. Otherwise, we will assign it to the maximum value, 255. We have also threshold trunk, and for every pixel at location X and Y, if the pixel value is greater than the threshold, it will be assigned to the threshold value, and if it is smaller than the threshold, it will just keep the same value of the pixel. So here, some parts of the image will be truncated, will be replaced by the threshold value. And we have threshold to 0, which acts similarly to the trunk, but here we're going to assign 0 if the pixel value is smaller than the threshold, and it will keep its own value if the pixel is greater than the threshold. Simple thresholding is pretty much simple, but it may not be good in all conditions, especially if the image has different lighting conditions. A better approach would be to use the adaptive thresholding, and here the algorithm calculates the threshold for a small region of the image, and then different thresholds will be calculated for different regions on the same image, and thus this approach will have a better robustness to varying lighting conditions. In OpenCV, we use the method adaptive thresholding, which takes the gray image as input, the maximum value, which is typically 255, and then the adaptive method type, and here we have two different types. It can be adaptive threshold mean C, where the threshold value calculated is the mean of the neighborhood area. So here is going to take the mean value of the neighborhood area of interest. And another adaptive method is to use the Gaussian method. And the threshold value is the weighted sum of the neighborhood values, where weights are a Gaussian window. It takes also a block size, which decides about the size of the neighborhood area, how many pixels you take in the neighborhood. And the constant C, it is just a constant which is subtracted from the mean or weighted mean calculated. You can see here in the image the impact of different thresholding. So you can see in the original image we have some shade distributed all over the image. And when applying global thresholding using simple thresholding, with the value of the threshold equal 127, is going to give this binarization of the image, which is not acceptable. However, if we use adaptive thresholding, so this is using the mean thresholding, and here we use Gaussian thresholding, so we can see Gaussian here provides a little bit better performance as compared to the mean. But probably this is not a rule, so it might depend from one image to the other, but here the adaptive thresholding is clearly better than the global thresholding. It has to be noted that thresholding is an important technique in computer vision, and this step is necessary in many applications such as contour detection. which is going to be explained in a future lecture. So now let's see how it works in practice. Let us consider the file image thresholding.py, where I'm going to present how to perform thresholding both using simple thresholding and adaptive thresholding. So this is the main function. I'm going to explain the code. So first we specify the image name. So I'm going to use two images, shapes and tomato. Okay, so let me start by tomato here. And then first of all, we need to read an image as a grayscale image. I have created the method read image. Okay, and you can see here, this is the method read image. It takes an image name, and here I specified a Boolean variable as gray. So if as gray is equal to true, we're going to read the image as a gray image. And for this, we can use cv2.imread, the same method that we used before. And then we specify the image name. This is the path to the image. And here we specify a flag that is called imread grayscale. So in this case, the image is going to be automatically converted into a grayscale image, even if it is a color image. If you want to read the image as a colored image, in this case, you can just either keep the default flag, or you can specifically specify that you want to use the flag cv2.imread_color. Okay, so in our case, we're going to use the flag imread grayscale just to read the image as grayscale image. If you have read the image as a colored image, in this case, you may need to use cv2.convert_image, and you can convert it to a grayscale as we did in previous videos. And here we're going just to show the image itself. So let me call this as image. And then we will take this gray image as an input to the method basic thresholding. Okay, and here I will specify the threshold value. So let's say the threshold value is equal to 115. We can change it actually. So I'm going now to disable the adaptive thresholding. And basic thresholding, it's going just to call the OpenCV method cv2.threshold. So this is the method I have explained in the slides, which take a gray image, an RGB image. So this one should be gray. And then the threshold value, which is an input here of the method that we define. The maximum value is equal to 255. And here we're going to choose threshold binary. So let's first choose threshold binary, and then we see what happens. So you can see now I'm going to display the image after that. So let's run the code, image thresholding.py, and here you can see this is the grayscale image, okay, and this is the basic binary image after conversion. So let's apply this one on the shape image. Going now try on the shape image. Okay, this is the grayscale image and this is the shape image. You can see now only the square shape was discovered. Why? Because this one, it has a high value of the threshold. So if we decrease the threshold value, or if we increase the threshold value, for example 200, so it becomes brighter. In this case, we can detect more shapes, as you can see, because we have considered brighter pixels in the thresholding operation. So here basically what we want to have a black background and a white, and the shapes are colored in white. In this case, what we can do, we can just invert, okay? So instead of using threshold binary, we can use threshold binary inverted, okay? And just running the same code, you will see now it's completely inverted. What was black becomes white, and what was white becomes black. And basically because later on we are going to use the thresholding for contour detection. In contour detection, we need to make sure that the background is black. So I'm going to keep the thresholding style to threshold binary inverted. So you can see with adaptive thresholding, we need to play a lot with threshold value in order to detect objects. And this is why adaptive thresholding is much better. So let me put this back at 115. And as you can see, only one shape was identified by the mask. And now we can use adaptive thresholding, okay, and here we can identify all the different shapes. We can find some holes here, but we can play with the value. For example, I will decrease the value of darker cells. So you can see with adaptive thresholding, we're able to detect the shapes contours here, but of course, with very low threshold values, all the shapes will be considered as black. So adaptive thresholding, it uses the method adaptive threshold, which takes the gray image and then 255 is the maximum value. Here I have used the Gaussian method for the computation of the adaptive threshold in every region. We used threshold binary inverted and the threshold value which was defined over here. Okay, we can also use the mean just to see what it looks like. Okay, so similar behavior. Now putting back the default value, so you can see with the mean we are still able to identify the different shapes. Let's apply this on tomato image. This is with binary thresholding and this is with adaptive thresholding. So you can see with adaptive thresholding, it really looks much better. So you can see here the effect of illumination. It is more negative with the simple thresholding and it is much better managed with the adaptive thresholding. So in summary, thresholding is a simple operation for image segmentation, which takes as input a gray image and produces a binary image. And this binary image is actually useful in several applications, in particular contour detection. So in the next videos, I'm going to talk about contour detection, which is also used in a more general context of object detection based on the colors. In this lecture, I'm going to talk about color filtering, which is an interesting technique in computer vision and image processing. Consider the following image, where we have a tennis ball that we would like to detect inside the image. It is clear that the tennis ball has a very specific color in the image, which is different from the colors of the other pixels. So we can use the color feature of the tennis ball in order to detect its location inside the image. And for this, we can use color filtering techniques. So color filtering is defined as displaying only a specific color in the image. And it is used in a wide range of computer vision applications, especially for detecting objects with specific colors. The algorithm is composed of 4 steps. First, we read the image as an RGB color image, and then we convert the image into the HSV color space. And you will see why HSV is more suitable for this type of applications. And then we define the upper and lower color ranges of the color of interest, and finally we create a mask based on the color ranges applied to the HSV image format. So let's see how it works in practice. So now this is the code of the color filtering. First of all, we open an image using cv2.imageRead, and then we access one of the images in the images folder. So I'm going to start with this one, but also we can later on try on different things. So here we're going just to show the original image. I can run the code to start. So this is the original image. And as I mentioned in the introduction, the first thing we need to do is to convert the image into the blue saturation value, HSV color space. Okay, so we need to convert the image into the HSV color space. And to do so, we will use, so I'm going to create a new image object called HSV, cv2.convert color. I will take the image and then cv2.color BGR to HSV. And let us show the HSV image now. Okay, so this is how it looks like. At this stage, you may wonder why we need to make the conversion. Okay, so let me first explain. So our problem is to detect the image ball using its color, and the color here is yellow. The problem with RGB color space is that it is not robust toward external lighting changes, and this is why we prefer to use HSV color space instead of the RGB color. Just to illustrate the problem, let's consider this grid with different red colors. So these red colors, if we use the RGB color space, they will have completely different values. So it's going to be very difficult to find a range of red values to which we are going to use to filter out the colors. However, using the HSV color space, we know that all the red values are ranging between 0 and 60 degrees. Okay, so this is now the representation of the HSV color space, which looks like a cone. So we have here the circle represent the U value, and it ranges from 0 to 360 degrees. Okay, so the values between 0 and 60, it corresponds to the red. So you can see now the red starts from 0, and then it moves until the value of 60 degrees. At 60 degrees, we start to have the yellow. This is the part of the yellow here. And then we move at 120, we start to have the green color. Okay, so the green color is between 120 and 180. At 180, we start to have the cyan color, which is this one, okay, and then the blue, and then the magenta. So all this circle here, it represents the colors. And this is very useful if we want now to filter out certain colors. For example, if we want to just have the yellow, we can have a mask applied to the values 60 and 120, for example. Okay, if we want to filter red values, we can use between 0 and 60. So you can see the HSV color space allow us to clearly define a bound for any kind of colors. And the other axes, they represent the saturation and the value. So you can think about the saturation as the amount of shade or the gray color that you do have in the color. So you can see when we move in this direction, we have more saturated colors. And the value, it represents the level of brightness. And these two values, usually they are encoded between 0 and 100 as percentage. So 0%, it means there is no saturation, and 100% means it completely saturated. And 0, it means very dark pixel, so it's black one, and 100 will represent the very bright pixels. So as such, the HSV color space is much more suitable than the RGB color space in order to perform color filtering, because the color bounds are well defined. Now there is one note that you have to consider when we work with HSV color space in OpenCV, is that it uses different ranges for the HSV color space. So in the previous slide, I have mentioned that the U is encoded between 0 and 360 degrees, but in OpenCV, we just encode the values between 0 and 180. So in this case, we need to define every range by 2. So this means that the red color will be defined in OpenCV between 0 and 30, and the yellow color will be defined between 30 and 120, and so on. The saturation and the values are not encoded as a percentage like it is in the standard representation, but they are encoded as values between 0 and 255. 0, it means gray for saturation, and 255, it means saturated color. And the value 0 means dark color, and 255 means bright color. So this is the convention that is being used in OpenCV, and we will be using in order to define the upper range and the lower range of our desired color. So looking at our problem now, we would like to detect a tennis ball, and a tennis ball has a yellow color. So now we need actually to select the color space in the HSV format that specifies the yellow color. And now based on this table, the value should be between 60 and 120. Considering the convention in OpenCV that the U is encoded between 0 and 180, in this case we need to divide this by 2. So the yellow will be defined between 30 and 60 degrees in OpenCV. So let's see how it works. Now, having understood why we need to use HSV format for color detection, let's now define the upper bound and the lower bound for the yellow color that we would like to filter in an image. So now we will find the upper and lower bounds of the yellow color, okay, for the tennis ball. So let us define the yellow lower color. So remember, in the standard representation of the HSV format, the yellow bound is between 60 and 120. And since we work with OpenCV, so we need to divide this value by 2. So it's going to range between 30 as the lower value, and the upper value will be 60. Now we need to define the saturation and the brightness of the lower bound and the upper bound. So the general rule here is that we need to choose low values for saturation and for the brightness in the lower bound, and higher values for the saturation and the brightness for the upper bound. So here we can choose, there is no actually a rule to follow, but it's kind of try and check operation. So we're going to just propose some values, and then if it doesn't work fine, you can tune them so that the color filtering will be as much accurate as possible. So let's choose the maximum values for the saturation and for the brightness in the upper bound. And now we need to use the HSV image format and the lower and upper bounds in order to define a mask. So I'm going to define the mask using the lower upper bounds of the yellow color. How can we do that? We can define the image mask, and we use the method cv2.inRange. It takes as parameter the HSV image and then the lower bound and the upper bound. Okay, so finally everything is done. We can just now print the mask using cv2.iAndShow. So we print the mask. And as usual, we will use cv2.waitKey 0 and cv2.destroy all windows after pressing the key. Okay, that's pretty much it. Now we are going to apply this algorithm on the tennis table 1, which is this one, and you will see 3 images: the original image, the HSV image, and the mask image. So what we expect to have is that the mask must show the yellow color as white and any different color as a black color. So let's run the application now. Now we have 3 images, as you can see. This is the original image, this is the HSV image, and this is the mask image. You can see now everything in the range. You can see here a little bit of yellow values, or similar to the yellow values. So maybe we can remove them by just playing with the saturation and the brightness. Let's do some work here. For example, maybe we can use higher saturation and a higher brightness. You can see now the performance looks a little bit better. We don't have these places now because maybe these colors here would have something similar to the yellow, but at lower brightness and lower saturation, it will also be selected. Let us also try some other images. So you can see here now, you have the ball selected, but also because some other places also have some kind of green color, so maybe we can actually improve this by reducing the value of the U in the upper bound. Okay, so for example, if I choose this value to be 50 only, we still have the values here. Okay, so we did some tuning in any case. You can choose also some other images to see the performance of the algorithm on other images. So you can see here, just filter this place. Maybe we can play with the hue and saturation in order to improve the performance. You can try on the image number 4 also. Okay, and here we have a very nice detection because we have really yellow color very well specified. And let's try the last image. Okay, it also worked pretty much fine. So you can see the performance will depend on the lighting conditions, but it's robust by the way. So we have applied on 5 images. 4 of them have a very good performance. So for the remaining image, we can actually tune a little bit more the upper and lower bounds in order to improve the accuracy of the detection. So to wrap up in this video, we have introduced the color filtering technique that allows to select a particular color in the image. And this technique is used for object detection when the object has a specific color in the image. It will be even nicer and more interesting if we are able to draw a circle around the ball, okay, in the mask image, so as to identify a contour of the image. And for this, we need to do contour detection, which is going to be explained in the next video. And now it is time to talk about contours or edge detection of an image. Edge detection, also known as contour detection, is an image processing technique that consists in finding the boundaries of objects within an image. And contour detection represents another alternative for image segmentation techniques to detect and identify objects in an image. In the previous videos, we have used color filtering techniques to identify objects that have specific colors. However, color filtering does not allow to find objects with any kind of colors. So contour detection provides another alternative that can be even more general. The contour detection technique works by detecting discontinuities in brightness. So an edge represents the borderline between a dark and the bright areas. And this is a useful tool for shape analysis, image segmentation, object detection, and recognition. So next we will see how to implement contour detection using OpenCV. But before, let's see what are the different steps that we have to follow. So first of all, we need to read an image that could be an RGB image, and then we have to convert this image into a grayscale image. Then we use thresholding to convert the grayscale image into a binary image like we have introduced in the thresholding lecture. And finally, we apply the method cv2.findContours on the binary image so that to identify all the contours in the image. So then we will have a data structure that will store all the contours of the image, and then we can process this data structure. For example, we can find the area of the contour, the enclosing circle, the perimeter, the moment, and the centroid point. It is important to note that contours follows a certain hierarchy in OpenCV. In fact, in an image, some shapes are inside others. Okay, so the outer shape is called the parent, and the inner shape is called the child. So, for example, here we can say that the shape 2A is actually a child of its parent, shape 2. However, it represents a parent to shape 3, and so on. So this is the shape hierarchy. And because of this, there are several ways on how to retrieve contours in an image. So the simplest way and the easiest way is to retrieve contours as a list. Okay, so retrieves all the contours, and in this case it doesn't create any parent-child relationship. It is just a list. Parents and childs are equal. There is actually no hierarchy between the different contours when we use the list flag. So all the contours are just contours. They belong to the same hierarchy level. We can also select only external contours. So if we use the flag retrieve external, in this case it returns only extreme outer flags or extreme outer contours. All child contours are left behind. And you can say under this law, only the eldest of every family is considered. So the third flag is the retrieve C-comp. And this flag retrieves all the contours and arranges them to a two-level hierarchy, external and internal. So external contours are considered as placed in hierarchy 1, and the contours of holes that are inside the objects are placed in the hierarchy 2. And finally, the fourth flag is the retrieve tree, which retrieves all the contours and create a full family hierarchy list from parent to child. So here we have parent to child relationship. So because contours will be considered as a tree, okay, and it can tell even who is the grandfather, the father, the son, the grandson, and so on. So these are the different contours available in OpenCV. And now it's time to see how it can be implemented. So let's see how it works. So let us get started with the simple example. We consider the file contours_detection.py. And here, let's go to the main function, which I'm going to explain. So first of all, we need to identify the name of the image, and then we will read the image. So here we will read an RGB image. So these are different methods that I have defined above. I'm going to explain them one by one, but just here to show you the different steps that we need to follow. Okay, so first of all, we need to read the image in RGB color, and then we convert the image into a gray color image, okay, taking the input, the RGB image that we have read previously, producing the gray image. And then using thresholding techniques, we need to convert the gray image into a binary image. We take as input the gray image that we find in the previous step, and then we produce the binary image. And here we have some flags, so whether we want to use adaptive thresholding or simple thresholding. After that, we will get all the contours from the binary image. So we will see how to implement this method. And finally, we draw all the contours of the image. So let's go one by one. First of all, we need to read the image. And this is pretty much straightforward. So we use just cv2.imread, where we put the image name. And here we have a Boolean variable. If it is true, we're going to show the image. Otherwise, we will not show the image. The second step is to take this RGB image as input to the method. Then we need to convert it to a grayscale image. And as before, you can use a Boolean variable here, whether we want to show the gray image or not. And finally, we need to return the gray image as an output of the method. So this gray image will be an input to the next method, that is convert gray to binary. And here we will use either adaptive thresholding or simple thresholding. So if you don't remember what is adaptive thresholding and simple thresholding, you can go to the lecture where we talk about thresholding techniques in OpenCV. So here there is a flag that we define called adaptive. If it is true, we're going to create a binary image using an adaptive thresholding. So here we can use either Gaussian or the mean adaptive technique. And these are the different parameters of the method. So we're going to use threshold binary, and this is the neighborhood region. Or the second alternative is that we can use simple thresholding using cv2.threshold applied to the gray image. And here we can specify 127 as the threshold value. Of course, we can change this depending on the performance we want to achieve on a certain image. And finally, using the show Boolean variable, whether we want to show the binary image or not. So I'm going to enable all of them, put them everything to true. The next method is get contour. So how to define get contour? We're going to use the OpenCV function find contours. Okay, so find contours, it's an OpenCV function. It takes a binary image as input, and then it will return three different variables. We will be interested to the second variable at index 1, contours. So contours is going to have a data structure that contains all the contours identified in the binary image. So in this example, we have used the flag tree. Okay, so the last function is called draw contour. Okay, that we'll call the OpenCV function draw contours. It takes the image here, okay, the contours that we have found from the binary image, and then we specify which contour to print, because the contour is like an array, so we can specify which index of the array to print. If we specify -1, it means we will print all the contours. We will draw all the contours in the image. If you press, for example, 0, it's going to display the first contour. If you choose the index equal to 1, it's going to display the second contour, and so on. -1, it's going to display all the contours. So this is the thickness of the contour. We're going just to have a line of thickness 2, and this is the color of the contour. Okay, you can specify any color. So here is 255, 0, 255, but it can be any other value. And finally, we will show the image after drawing the contour on top of that. So let's apply now this program. We run now contour detection, and you can see now all the contours were now displayed. Okay, so this is the RGB image, this is the gray image, and then we create the binary image, and finally we draw the contours on the initial image. Of course, here, as I mentioned, in principle, we should have a background that is black. So we're going to use the threshold binary inverted to have black contour. Okay, so the result will be the same. Here we have a black background and the contours are in white. So here we have used the flag true, it means adaptive. So we can also use with the simple thresholding. So you can see now simple thresholding, not all the areas were detected. So only detected this one and this one. So only 3 borders were detected. Again, adaptive thresholding might be more appropriate to work with. Of course, we can apply on other images like tomato image. Okay, so you can see here now, you can find the contour of the image. So this is using the static thresholding. You can change this to adaptive thresholding, and again. So you can see with adaptive thresholding, okay, maybe we need to play a little bit with the value of the regions, because it's a little bit small, but it was able to detect actually all the borders in quite efficient way, especially there are some internal borders here, maybe playing with the value of the threshold here. Okay, so we have a different behavior, okay, by increasing a little bit the threshold. So to summarize, it is possible to find the contour of an image using the OpenCV function find contours, which must be applied to a binary image. So if you have an RGB image, you need to convert it to a grayscale, and then you convert it to a binary image using one of the thresholding techniques, whether simple thresholding or adaptive thresholding. And finally, you can call the draw contours method of OpenCV to draw all the contours. But what if we want to draw only particular contours, not all of them? Or we want to find the area of the contour. This is also possible, so I'm going to switch to the other file that is called contours processing, and basically we follow the same steps. We need to read the RGB image, then convert it to a gray color, then convert it to a binary color using one of the thresholding techniques, and then getting all the contours using find contours. We do all in the same way. So this is draw contour if you want to draw all the contours, but instead of drawing the contours, I would like to process them. So I create here a method called process contours, which takes the binary image and the RGB image here, and also the list of contours. So here processing the contours can be done in several ways. For example, we can create a for loop that will go through all the different contours in the contours data structure. So for every contour in the data structure contours, we can print the area using the method contour area C, and then the perimeter using arc length C and the flag true. We can also find the minimum enclosing circle. Okay, so minimum enclosing circle is defined by the XY coordinate of the center and also its radius. So we will use this radius in order to draw a circle around the contour, and this will enable to draw a circle on detected objects in the image. Okay, so we have different functions that we can run on the contours, like contour area, arc length, minimum enclosing circle. So it's possible now to draw the contour using RGB image. So this is the contour, selected contour here. So we pass it as an array here, and we use the index -1 to print all the contours. In this case, we have only one contour in the array, and then we specify the color and the width of the line. So I'm going to draw the contour on the same image, original image, RGB image, and also I will create a black image where just to print the contours. So I will have black image with only the contours drawn on that. So if you want to draw a circle on the contour, you need to find the center point. And for this, we can use a method that will allow us to find the center point. So what is the strategy to find the center point? So the common way to find the center point of a contour is to use the method of OpenCV called moments. We're going to calculate the moments of a contour, and then by definition, the center point with coordinates Cx and Cy is defined by the moment at index M10 divided by the moment at index M00, and Cy is defined by the moment at index 01 divided by the moment at index 00. It is not a problem if you don't understand very well the concept of moments, but you can just use this formula as it is whenever you want to calculate the centroid of a contour. Of course, here we need to make an if condition to make sure that we will not do this division only if M00 is different from 0. Otherwise, we're going to skip it. So this is by definition how we can calculate the center point. So this method get contour center, we can call it here, get contour center. So we pass the contour as an input parameter, and then we will expect to have Cx and Cy, which are the coordinates of the center point. And finally, we can draw a circle on the RGB image and also on the black image to specify the detected object. We can print the different parameters like the area and the perimeter here. And finally, after exiting the for loop, we can print the number of contours and showing the RGB image on the black image to show the contours around them. So you may wonder what is the advantage of this method as compared to the previous draw contours, which draws all the contours. So here actually we can do some restrictions on which contour we want to draw. For example, it's possible to make an if statement here. For example, if the area is greater than 10 or any certain value, we're going to print the contour. Okay, so for example, very small contours, we may ignore them. So it can be used to filter out some of the contours in the image. Okay, so let's run now this program. It's called contour processing.py. Let me run it again. Okay, so these are the different images. This is the original image here. You can see that we have here the number of contours is equal to 5. 1, 2, 3, 4, 5. Every object detected has specific contour. Okay, and you can see a surrounded circle around every object. This is the black image that we have created that only draws the contours. And this is now the gray scale image. And this is the binary image. So you can see the different steps. We start from an RGB image. Okay, and then we create, then we create a grayscale image. Based on the grayscale image, we create the binary image. Okay, using the binary image, we can run find contours, and find contours allow us to find the list of all contours and then finally to draw them